Welcome to Chemsphere Hub. Today's lecture is on fluorescence spectroscopy, which is most of the sensitive and powerful analytical techniques used in modern chemistry, biochemistry, and environmental sciences, and in medical diagnosis. In this lecture, we'll move step by step from basic concepts to advanced applications of fluorescence spectroscopy. I will explain not only what is fluorescence, but also why it occurs, how it is measured, and where it is applied in real life. By the end of this lecture, you would be able to confidently explain fluorescence spectroscopy in research discussions and presentations. And after completing this lecture, we will be able to define fluorescence spectroscopy clearly, explain the theory using the Jablonski diagram, describe the instrumentation of a fluorescence spectrophotometer, and discuss its applications, advantages, and applications and limitations. So keep these objectives in mind. We will move forward. Fluorescence is very important technique as it is very useful in the advanced applications. In fluorescence spectroscopy is used to identify molecules and analysis during different analyses. Uh, now we will discuss about spectroscopy. What is spectroscopy? That is the basics of fluorescence spectroscopy. That spectroscopy is the study of interaction between electromagnetic radiation and matter. So spectroscopy to study that how spectrum is produced and how the electromagnetic radiation interact the matter. So when radiation interacts with atoms or molecules, it can be absorbed, emitted, or scattered. So this interaction give the very valuable information about molecular structure, about the concentration of sample and the environment. So the spectroscopy is very useful analytical technique that is used to identify the molecular structure, its concentration, and so we can also study the unknown compounds, unknown molecules. Fluorescence spectroscopy belongs to this broad family of spectroscopic techniques, and it is very important analytical tool to identify the any unknown compound sample. As we are studying the basics of spectroscopy, so spectroscopic techniques are broadly classified in absorption spectroscopy, in emission spectroscopy, and scattering techniques. As these different patterns, different methods are used in different spectroscopic techniques like UV, visible, and infrared spectroscopy use the absorption methods. However, the fluorescence technique is an emission technique, making it fundamentally different and more sensitive as compared to other techniques. If we see that fluorescence spectroscopy is a type of emission spectroscopy, instead of measuring absorbed light, we will measure the emitted light, which produces the fluorescence, which allows detection of extremely small concentration. And fluorescence is produced means the emission of light is produced. In the case of fluorescence spectroscopy, the light is emitted, which so we will measure the emitted light, which will detect the extremely small concentration of sample. That is why the fluorescence spectroscopy is preferred for trace analysis. Trace analysis means it is sensitive so that it can analyze the very minute amount of sample. So it is very important technique, fluorescence spectroscopy, as the name shows that the fluorescence is produced, that is the emission of light. Now, what is luminescence? Luminescence refers to the emission of light from a substance without heating. It occurs when excited electrons return to the lower energy level. So, emission of light takes place. That luminescence phenomena takes place when the emission of light takes place from the excited molecules, not from the heated molecules. So without heating, luminescence process takes place, and it occurs when excited electrons return back to their lower energy level. So luminescence is comprised of two processes, that are fluorescence and phosphorescence. There are two important phenomena, there are two important aspects which can be studied in detail. And fluorescence is the immediate emission of light after absorption of radiation. This emission occurs within nanoseconds, and this is fluorescence. However, in case of phosphorescence, the phosphorescence takes a long period for the emission of light, and it is a very slow process, and it is the difference of fluorescence and phosphorescence. If we see that fluorescence is the immediate emission of light after absorption of radiation. So we can understand through the definition that if light is absorbed through the radiation, then the immediate emission takes place. So that by the absorption of light, electron jumps into the higher energy state. And when it jumps to the higher energy state, and when it comes back to lower energy state, that the emission of light takes place. And in case of fluorescence, it is the immediate emission of light that takes place. So it takes place within nanoseconds. So it is very immediate immediate emission, and it takes place within nanoseconds, very immediate process. And once the excitation source is removed, fluorescence stops instantly. The rapid response is a key identifying feature. So as we have discussed that it is the absorption of light takes place through the absorption of radiation, and after the absorption of radiation, and the electrons jump to the higher energy state, and when they back to the lower energy state, then the fluorescence takes place, and it is the immediate emission of light. When a molecule absorbs a photon, an electron is prompted from the ground state to an excited electronic state. When a molecule absorbs light, when a molecule is radiated, then the light or radiation is absorbed, and it will go to the excited state. It will absorb the radiation and it will absorb the photons, and it will go to the higher or excited electronic state, and this excited state is unstable. So molecule want to become stable, so it molecule quickly seeks the stability to lose by losing the excess energy, and this is energy absorption process that become the electron become unstable, and it goes to the excited energy level. And now we will discuss the energy emission process in detail. Before emitting light, the molecule loses some energy as heat through vibrational relaxation. As a result, when emission occurs, the photon has lower energy and longer wavelength than the absorbed photon. So, it is discussed that when a photon is absorbed, then electron become unstable, then the molecule is in excited state and it is become unstable, and it wants to become in stable condition. So some of energy is utilized in vibrational processes, in vibrational relaxations, and then the emission occurs, and the photon will have then the lower energy state, because the some energy is utilized in the vibrational relaxation process, as it is molecule loses some energy as heat through vibrational relaxation, and as a result the emission occurs. The photon has lower energy and longer wavelength than the absorbed photon. So it is very clear from the energy emission process. Now if we discuss the difference between the fluorescence and phosphorescence. Fluorescence involves the singlet to singlet transitions and is very fast. However, phosphorescence involves triplet state and is very slow and straight. Fluorescence stops immediately, as the fluorescence, in case of fluorescence, the photon is immediately returns to the lower energy state. However, in case of phosphorescence, it continues even after removing excitation. As phosphorescence involves the triplet state and is very slow. However, fluorescence involves the singlet to singlet transition. So it is very fast, because the electron has to come back in singlet to singlet state. So it is very fast process as compared to the phosphorescence process, which is a slow process. Now we will discuss the electronic energy levels. Molecules possess electronic, vibrational and rotational energy levels, and fluorescence mainly involves electronic transitions which are accompanied by vibrational changes producing broad spectral bands. As we already discussed that when molecules are in excited state, photons, then they also lose some energy as heat during the vibrational and relaxational processes, and when they come back, then they have lower energy level, and so they have longer wavelengths as compared to the photon which was absorbed, which has high energy level and shorter wavelength. After excitation, the molecules undergo vibrational relaxation. After when the molecule absorb the heat, absorb the energy by radiation, then it goes to the higher energy level, and there the vibrational relax, then it become in unstable state and it wants to become stable, so it undergoes vibrational relaxation and it loses energy as heat. So excess of energy is lost as heat before the occurrence of emission, that is vibrational relaxation. So after excitation, the molecule undergoes vibrational relaxation. This is a non-radiative process, meaning no light is emitted and energy is lost as heat to surrounding molecule. So it is very clear that it is a non-radiative process, as no light is emitted, no fluorescence process takes place in this uh, process, and only the vibrational relaxation takes place and excess energy is lost as heat to surrounding molecules, not the emitted light takes place. Now we will discuss the internal conversion, which is very important. Internal conversion is another non-radiative process. As one non-radiative process is the vibrational relaxation, and the second non-radiative process is inter internal conversion. So, no, internal conversion is a non-radiative transition. Here energy is transferred between electronic states of same spin multiplicity and further reducing energy before emission. So before the emission, different processes takes place and energy is transferred between the electronic states of same spin multiplicity, and this is internal conversion process. It is a internal conversion process and it is a non-radiative emission process. Non-radiative process, in this case no light is emitted, and it takes place before the emission to occur. Now it is inter-system crossing process that occurs when an electron moves from a singlet state to a triplet state. So it is termed as inter-system crossing phenomena. It is termed as inter-system crossing phenomena. This process leads to phosphorescence rather than fluorescence. If inter-system crossing phenomena takes place, then from singlet state to triplet state, that it will result in the phosphorescence process. Only in this case the fluorescence process will take place and not the fluorescence process. Now it is a representation of a diagram, the Jablonski diagram, that visually represents all these processes. It shows absorption, relaxation, internal conversion, intersystem crossing, fluorescence and phosphorescence in one diagram. This diagram is central to understanding the fluorescence theory. As we can see that S shows the singlet system and T shows the triplet system. And when the energy is excited, electrons, it takes the energy, it goes to the from lower to higher energy levels. As we can see that it goes to the higher energy level like this one, and these are some features which takes place as these are the black lines which shows the energy levels. And absorption, this is absorption of energy which takes 10 raised to minus 15 seconds. The absorption takes almost 10 raised to minus 15 seconds. And this shows the fluorescence. This is the fluorescence phenomena. So we will discuss all these phenomena as we see that before fluorescence emission we will discuss the internal conversion process and vibrational relaxation and intersystem crossing phenomena. Internal conversion as one singlet state to intersystem and other singlet state. This is internal conversion. And here some energy before emission is used in the vibrational relaxation. This is vibrational relaxation process occurs, and it takes the 10 raised to minus 12 to 10 to minus 10 seconds. And internal conversion process takes to 10 raised to minus 11 to 10 raised to minus 9 seconds. And these phenomena processes occurs before the occurrence of fluorescence or phosphorescence. And in case of fluorescence, after the internal conversion and after the vibrational relaxation, these both are non-radiative processes, and after these the fluorescence process takes place. After these the fluorescence process takes place, we takes 10 raised to minus 10 to 10 raised to minus 7 seconds, and it is very immediate process. And as we can see that the energy is absorbed from here to, and it is excited to higher energy level. So it is the more energy is absorbed. However, the fluorescence process takes place here, and some energy is utilized as internal conversion, and other some energy is utilized in vibrational relaxation, and it is not emitted. It is not radiative process. And when it comes to this state, then the fluorescence process will occur, and it will the system will remain same from singlet to singlet state. The fluorescence process will occur, and it is immediate process, and emission of light occurs in fluorescence process immediately in 10 raised to minus 10 to 10 to minus 7 seconds. Now, however, in case of phosphorescence process, it takes longer time as 10 raised to minus 6 to 10 seconds. Why it takes much time as compared to fluorescence? As this phenomena, this important phenomena, intersystem crossing, as the system from singlet is transferred to triplet system. So it takes time from here to here, and it takes time, and intersystem crossing takes also time, 10 raised to minus 10 to 10 to minus 8 seconds. And then the phosphorescence process takes place, and because it is there are different states, triplet system and singlet system. So it takes more time because there is are difference in systems. So phosphorescence process takes much time to appear as compared to fluorescence process. So we discuss the all processes very in detail. The fluorescence always occurs from the lowest vibrational level of the excited singlet state, as we can see in the diagram, and this explains why emission wavelength is independent of excitation wavelength. As we discussed that excitation wavelength and emission wavelength will be different, as the excited molecule takes different energy, and after going through vibrational relaxation and internal conversion, the fluorescence emission wavelength will be different, and this explains why emission wavelength is independent of excitation wavelength. Now we will discuss the Stokes shift. The difference between absorption maximum and emission maximum is termed as Stokes shift. It occurs due to energy loss before emission, as the energy is lost during the internal conversion and during the vibrational relaxation processes. So the Stokes shift shows the difference between the absorption maximum and emission maximum. Now we will discuss the importance of Stokes shift. A large Stokes shift reduces overlap between the excitation and emission light, as if there will be a much difference of wavelengths of light. So large Stokes shift reduces the overlap between the excitation and emission light. This improves sensitivity and reduces background interference. So if less Stokes shift present, then the excitation and emission light can be overlapped, so that it will minimize, it will reduce sensitivity, and in case of large Stokes shift, that will reduce the overlap between the excitation and emission light, and this will improve the sensitivity and reduces the background interference. Now we will discuss the fluorescence quantum yield. Quantum yield measures fluorescence efficiency. It is defined as the ratio of photons emitted to photons absorbed. As the photons that are absorbed are of high energy, and have less shorter wavelength. However, the photons that are emitted have low in energy levels, and they have longer wavelengths. So ratio can be found out by fluorescence quantum yield, and it is defined as the ratio of photons emitted to absorbed photons. Now we will discuss the factors affecting the quantum yield. There are different factors which affect the yield, and the quantum yield depends upon the molecular structure, solvent, temperature and presence of quenchers. As we can see by the molecular structure, the quantum yields can be affected by the molecular structure, the solvents which are present, and the temperature. And rigid molecules usually show higher fluorescence. So factors are very important which can which can affect the quantum yield. Now we will discuss the fluorescence lifetime, that is the average time a molecule remains excited before the emission. So it is the lifetime, that how much a molecule remains excited before the emission. It is independent of concentration and intensity. It does not depend upon the concentration and intensity. It is independent of the concentration and intensity. So fluorescence lifetime is the average time a molecule remains excited before it gets emitted. Now, importance of lifetime measurement. Lifetime measurements help study molecular interactions, quenching and environmental effects. So they are widely used in biological research. If lifetime measurements is very useful to study the molecular interaction, the quenching effects and the environmental effects. So lifetime is measured, and that is very important. So lifetime is measured so that the biological research that is used in very much in biological research. If we discuss about the instrumentation of fluorescence spectrophotometer, it consists of a light source, excitation monochromator, sample cell, emission monochromator and detector. So light source, monochromators and detector systems are very important in case of fluorescence spectroscopy. And two types of monochromators are used. One is excitation monochromator and the other one is emission monochromator. Now we will discuss the light sources which are very important. As xenon arc lamps are mostly used because they provide continuous UV visible radiation. And mercury lamp is also very useful. Xenon lamps are very important, and mercury lamps are also very important, that are used in the fluorescence spectrophotometry. And lasers are also very important, that are used in advanced research. They are also very important. As we have discussed in the instrumentation overview, that there are monochromators are present, and there are two monochromators are present. And one is excitation monochromator and the other one is emission monochromator. The excitation monochromator is that the as the monochromator is is used to become the wavelength into a single wavelength. So the excitation monochromator selects the wavelength that excites the sample, because for the excitation of sample the and to select the wavelength, the excitation monochromator is used, because this monochromator selects the wavelength that excites the sample, so it is termed as excitation monochromator. It is used in diffraction gratings for wavelength separation. It is very useful. And if we see the emission monochromator selects the emitted fluorescence and removes scattered excitation light. As when the during the emission, then the emitted fluorescence light wavelength is selected, and the other wavelengths which are they are present due to scattering of some molecules that are removed by selecting the emitted light only, and so the emission monochromator is used that selects the emitted fluorescence and removes the scattered excitation light. Sample cells that are used in the samples are placed that can be made of quartz. So quartz cuvettes are used because glass absorbs UV radiation. So glass cuvettes are not used, and quartz cuvettes are used. And so to emit the effect of UV, so that the no light is absorbed as the glass absorbs the UV radiation. So quartz cuvettes are used to avoid the UV absorption, and proper concentration is analyzed. Detector systems are comprised of photomultiplier tubes that are used due to their high extremely sensitivity. They can detect very weak fluorescence signals. They are very useful photomultiplier tubes, and they are very sensitive detectors, and they have very high sensitivity. So detector systems is comprised of photomultiplier tube, and they have very high sensitivity, as it can measure the very low concentration. They can detect very weak fluorescence signals, so they are very sensitive detectors. What is right angle detection? The detector is placed at 90 degrees to the excitation beam. It is very important uh, to place it at 90 degrees. It is very important to place it at 90 degrees. It is very important to place it 90 degrees, as it is very important, and it minimizes the scattered effect. So only the emitted light is measured and scattered light is omitted. At low concentration, fluorescence intensity is proportional to the concentration, and at high concentration, quenching occurs. So at low concentration, fluorescence is very important, and quenching takes place at very high concentration. So low concentration is very detected, is very useful. Fluorescence technique is very useful to identify trace concentration, very minute concentration. It is very important. Effect of concentration is very important in fluorescence spectroscopy. Inner filter effect that occurs when excitation or emission light is reabsorbed. That is inner filter effect. This reduces measured intensity. As the light is reabsorbed as the excited light or emitted light, if emitted light is reabsorbed, then the intensity can be reduced. As some molecules only show emission, and however the others emitted light is reabsorbed, so the intensity will be reduced of the sample. Effect of solvent. Solvent polarity and viscosity affect fluorescence intensity and wavelength. And polarity and viscosity are very important while selecting the solvent, as it can it can affect shifts in emission wavelength. So solvent effect is very important, as the solvent itself should not give the emission light, or it should not interfere in the emitted wavelength. So that it should be very careful while selecting the solvent during studying the fluorescence spectroscopy. And pH is also very important while studying the fluorescence effect. pH changes the ionization states of molecules, altering the fluorescence. And this is useful in biochemical sensing. As pH changes the ionization states of molecule, so it will affect the fluorescence. So intensity also varies by the effect of pH. So it is very useful in biochemical sensing and in the selecting the pH. Now we will learn about the temperature effect. As increasing temperature increases coherence and reducing the fluorescence intensity. As if the temperature is higher of the system, then it will reduces the fluorescence. As the more coherence takes place, so fluorescence intensity becomes decreased. And we can say that quenching can be dynamic or static. It provides information about molecular interactions. So the process of quenching can be dynamic or it can be static. It provides about the molecular interaction, so it is very important. Fluorescence spectrophotometry is very important. It is a powerful analytical tool that is useful in the application of chemistry. It is used to study the trace analysis in the reaction monitoring, as it can be used to identify the impurities, and it is very powerful technique which can used to analyze the sample in very minute concentrations, in very trace analysis trace, so that as if the concentration is very low, Then the fluorescence is very important, and fluorescence spectroscopy is very important in identifying the trace molecules in a sample, and impurities are also present in very small amounts, so they impurities can also be detected by the fluorescence spectrophotometry. So it has major and wide applications, and it is a powerful technique in the analysis of chemistry. It is also a very helpful technique in biochemistry and medicine related fields, and they are used in protein studies and enzyme studies. They are very helpful in DNA analysis and imaging and diagnosis, as the trace concentrations of a sample is studied in fluorescence spectroscopy. So in case of biochemistry or in case of medicines, if there is present a minute concentration, if there is present small concentration, the fluorescence technique is very sensitive technique that can detect the sample of very low concentration or very trace amount of sample can be detected, and it is very powerful technique which is used to study the biological molecules like protein and enzymes, and they are very powerful technique in studying the minute, and is very sensitive technique that can be used in the DNA analysis. It can be used in imaging and different diagnosis patterns, and it is very helpful tool, and it is powerful tool. The fluorescence spectroscopy is very powerful tool to detect the study, and now we will discuss its application in the environment, in different environment related analysis, as it is very helpful in the pollution detection, and it has also wide application in pharmaceuticals as in drug analysis, already discussed, and in environment there are water quality monitoring, as we can see that as a toxins, as a toxic substances, as a pollutants, there is if a minute or low concentration is present, then even that can also be detected by the fluorescence spectroscopy. Fluorescence spectroscopy is a very powerful tool in the detection of very less concentration, so it can also detect the pollutant concentration. It can monitor the water quality. It is very useful in the pollutant detection, and it is also very useful in the water quality. And if we analyze the water, so the quality of water can be checked. We can check that any impurity is present in trace amount. If any impurity is present in trace amount, that can be detected by the fluorescence spectroscopy, as fluorescence spectroscopy is a very powerful tool while studying the different effects, different pollutants, different water quality parameters. We can see that the if we see that the compare it with the UV visible spectroscopy, it is much sensitive. It has higher sensitivity as it has a low detection limit. So it has high sensitivity, because any technique that detects the lower concentration that will have the more sensitivity. It has various advantages, like it includes the high sensitivity and selectivity. It is non-destructive in nature. It is as it don't cause the destruction. It is very selective and it is very high sensitivity in nature. It can measure the low concentration. So it is very sensitive and selective. If we see the limitations, so limitations include the quenching and applicability only to the fluorescent compounds. So the fluorescent compounds can only be detected, and it is very important and also relevant to the environmental sensitivity. It is its limitation, so that only the fluorescent compounds can be studied in very low concentration. It is a very powerful emission technique and it has wide scientific applications. Fluorescence spectroscopy is a highly sensitive and versatile analytical technique. Its applications span chemistry, biology, medicine, and environmental sciences, making it an essential tool in modern research. It is very important and powerful technique that it is used in modern analysis in advanced research. It is an important analytical technique. Thanks. Thank you very much.